So in this video, we're going to look at the curl of a vector field. So given any vector field f, which is here I'm looking at a 3D vector field, it works because the curl really applies to 3 dimensions, strictly speaking. So basically, the curl of f, where the vector field is in R3, basically, is defined as follows. So we use curl of f in small caps, okay, and then from a mathematical operator perspective, so the curl is an official operator, but in the practical way to actually calculate the curl, because that doesn't tell us what the operations actually are. Basically, the curl is in fact the cross product of nabla and whatever vector field you have, which means essentially that you have ijk partial by partial x, partial by partial y, partial z, and then you have your p, q, and r, which are functions of x, y, and z. So this is basically the way we calculate it. And of course, when you work it out, it turns out to be bad. So, or of course, as I said, you can also write it as just without the ijk's. All right. Okay. Let's look at an example. So here's an example. This vector field, and we want to find the curl of f. The curl of f, of course, will be. So this is the determinant we have to calculate, and that turns out to be equal to, as we calculate that, it's going to be the y derivative of this, which is 0, minus the z derivative of this, which is 2yz. Okay, so that'll be our first component. So if you like, we can put an I here. Then minus, let's see, j is gone, so x derivative of z minus 0. Okay, and plus we'll have the last one, the k, which is the x derivative of this, which is 0, y derivative of this, which is minus the x. Okay, so that turns out that that's going to be, in fact, minus 2yz and minus z and minus x. So that's the curl of f. Right, so the curl of the gradient of f, curl of grad f, some small f which is a function of 3 variables, and which is of course continuous up to second partial derivatives. If it's the zero vector, it's always the zero vector, the curl of the gradient of f. In addition, we have a very interesting and useful idea, which is if the curl of f, a vector field, is the zero vector, then f is a conservative vector field. Now, we've already looked at the idea of conservative vector fields earlier. You would have seen it in line integrals and earlier videos in this series of vector fields. But this is a very nice test. Otherwise, as you know, you have to look for the potential function to prove. And if the potential function exists, then we say that the vector field is conservative. But here, we have a very quick test which can tell us if a vector field is in fact conservative. So in our example here, this is a non-zero curl. So this means that this vector field here is not a conservative vector field, because what we get here is not the zero vector. So here's an example. Let's try to see if this vector field is conservative. So we go with the as usual. So that turns out that it's going to be, in fact, the y derivative of this, which is 6 xy z squared, minus the z derivative of this, which is also 6 xy z squared. That's 0. And then we have the second component is going to be negative of, so the x derivative of that, is going to be 3y squared z squared. Okay, so 3y squared z squared, and then we have the z derivative of this, which is going to be 3y squared z squared as well. So that makes that 0, the second component. And the third component then is the x derivative of 2xyz cubed, which is 2yz cubed, minus the y derivative of this, which is also 2yz cubed. So that's equal to, in fact, 0, 0, 0, and the 0 vector. Therefore, f is a conservative. So f is a conservative vector field. Now that we know it's a conservative vector field, we can go ahead and calculate or compute the potential function as we have shown and done earlier in the previous videos. Okay, we'll stop here.